Okay, so today we're going to prove that uncountable ordinals exist. There's a way to prove this, like if we had access to all the theorems that we are going to prove in this course, you can simply prove that uncountable ordinals exist by a simple argument as follows. Every set can be well-ordered. Every well-ordered set is isomorphic to an ordinal. And uncountable sets exist, therefore uncountable ordinals exist. That would be a proof, but in order to do this proof, we have to prove several things, such as every well-ordered set is isomorphic to a unique ordinal, which we're going to prove today, so that's fine. But we're not going to prove that every set can be well-ordered until section 8 or something, until the section about cardinal numbers. But the point is, like, this proof uses the axiom of choice to show that every set can be well-ordered, and that uncountable ordinals exist can be proven without the axiom of choice. So the proof I just described actually uses an axiom that we don't really need. So in order to prove that uncountable ordinals exist, we will introduce the notion of an Hartog's number, but before that, let me just go over the axiom of replacement, because I was not so happy with my own performance last time about this, because apparently I made little mistakes while writing the formal statement. I fixed that. I remember that I had fixed these like last lecture, but I just want to go over this again, okay? So because you already know what this is, this time I'm just gonna cover this quickly, okay? So let phi of xy be a formula that defines a class function. Remember, defining a class function simply means that for all x there exists a unique y such that this holds. Then for all sets A, there exists a set B, which is the image of A under this class function. Over here I am using, while stating axiom of replacement now, I'm using all the terminology I introduced last time, like the notion of a class function, what it means, and the notion of being the image of some set under such a class function. And formally this is written as follows. So we have this, implies that for all A, there exists B, for all Y, Y is in B, if and only if there exists X in A. So this was one of the complicated axioms of CFC in terms of the complexity of the statement. And this is a formal statement. You need not know this, know the meaning of this. What this says is, this simply says phi of xy defines a class function on the class of all sets, meaning the following. For all x, there exists some y for which we have that phi of xy holds. Okay, so for every set x, you can find some set y such that this holds. And not only that, for any x, you can find such a unique y. So if for any x you have y and y prime for which you have these two holding, then y is actually y prime. okay? The only reason I'm restating this is the statement I wrote last time. The only reason I'm restating this is apparently I just put this at the beginning last time and I erased and said that like this direction already follows from the rules of first order logic. Well, that's not true, as is. If you put some extra statement here such as and phi of xy, then the other direction, there's no problem with that direction, but like you can't put this because that would make it, well, that would make it false, okay? So that we don't have that arrow. This is simply supposed to say that the y for which phi of xy holds is unique, okay? So it says as that, and over here we put double arrows, that's fine. This simply says the image of, if you denote the class function defined by f sub phi, this simply says the image of A under this class function is B, and my remark from last time is true. Like you can actually see that there are statements of this where you only have this direction, and that's the same as putting, okay, this time let's get it right. This, okay? So if you just take this form and simply assert the existence of a set B for which this holds, the other direction can be proven as well, because if you have such a set B, you then apply the axiom of separation to B and take the elements of B which are in the range of this class function, and that would give you the subset for which this holds, okay? So I'm just going to introduce this form. I want to go over this because, as you know, time to time I make these small mistakes which I fix in class, but this was towards the end, so I just want to make sure that we're on the same page, okay? But the point is you don't have to know this formal statement, just know the meaning of axiom of replacement. If you have a formula in the language of set theory which defines a class function, meaning that it takes every set to a unique set, so it behaves like a function, then the image of any set under this class function is a set, okay? Anyway, that's that. And using this, we prove the existence of the ordinal, which I called omega plus omega. It was the second limit ordinal. We defined the notion of a limit ordinal as far as I remember. Now let's prove a very important fact, which is the following. Let's start today's actual lecture. So are there any questions about this? No? Okay. So let W less than be a strictly well-ordered set. Then there exists a unique ordinal alpha such that this well-ordered set is isomorphic as well-ordered sets to this ordinal. Okay. So let's prove this. What this says is, remember when we introduced the ordinal numbers, I said that the motivation was to represent well-ordered sets with certain special sets which were the ordinals, and this is like what it means for ordinals to represent well-ordered sets. Every strictly well-ordered set is isomorphic to a unique ordinal, okay, as strictly well-ordered sets. So when you need to talk about well-ordered sets, you can simply work with ordinals up to isomorphism, okay? So let's prove this. Okay, so for any element of W, let less than subscript W denote the following relation. Sorry, this is less than intersection predecessors of W cross predecessors of W. Okay, so remember that if you have a strict well-ordered relation, if you restrict it to a subset, it's still a strict well-ordered relation. This was one of the exercises. So take any element, restrict your attention to the predecessors of that element. So you simply look at your strict well-ordered relation, but only on the set of predecessors of W. This is still a strict well-ordered relation, and this is the symbol I'm going to use to denote this strict well-ordered relation. Okay. Now, consider the following set. Take the set of all elements of W for which you have that its set of predecessors together with this restricted relation is isomorphic to some ordinal as strictly well-ordered sets, okay? So you take all the elements of W such that this guy is isomorphic to an ordinal. Now, this set is clearly non-empty. Why? For example, the least element of, well, okay. Never mind. There are two cases. I mean, this may be empty. Either W is empty or not. If W is empty, this statement is true, okay? Because if this is empty, then it's already isomorphic to the ordinal 0. If this is not empty, W has a least element. And now this is not empty because if you take the predecessors of the least element, this will be the empty set, and it's isomorphic to the ordinal 0, so this will be non-empty in this case. So let's see. One thing to observe before we proceed, let's say that I claim that, okay, let me write down the statement, then I'll explain the claim. Clearly, for each W in W, there is at most one alpha such that, alpha sub W such that this is true. So I claim the following. If you take in a W in W, then there is at most one ordinal for which this holds. Why? Because let's pretend that this is isomorphic to another ordinal. Okay? Then these two ordinals would be isomorphic. But these are, like by definition, strictly well-ordered sets. Given any two well-ordered sets, what can you tell me? One of them is an initial segment of the other, or they're isomorphic, they're the same. Well, these two are ordinal numbers, which means that either they are the same, one of them is an element of the other, or the other one is an element of the other one. It cannot be the case that this is an element of this, for example, because in that case, this would be an initial segment of this, which is isomorphic to itself, but no well-ordered set is isomorphic to a proper initial segment of itself, okay? So just using the fact that no well-ordered set is isomorphic to a proper initial segment of itself, you can prove that this guy cannot be isomorphic to two distinct ordinals, okay? So for every W, there's at most one guy such that this is true. And for each W, I'm just going to denote this ordinal by alpha sub W, okay? Now, by axiom of replacement, which I'm going to note by RE, the collection omega, which consists of all such alpha sub W is a set, okay? So what I do is, let me write this properly, consists. So what I do is, I want to take all such alpha sub omegas and put them in a single set together. I can do this. Why? By axiom of replacement. What I'm doing is, pretend that I wrote this huge formula which says the following. If my set is in not W, then I'm going to map it to the empty set, okay? My formula holds if this Y is the empty set and X is an element of W. If my element, X is not an element of W. If my element comes from W, I will look for such an alpha. If it exists, I'm just going to map W to that alpha. Otherwise, I'm just going to map it to, let's say, the empty set. This formula will define a class function, okay? It takes any set to a unique set. So the image of W under this class function is a set, but that image is exactly this collection I'm looking for. It's the collection of all such ordinals. Now, I claim that this is itself an ordinal, okay? We claim that omega is an ordinal. Now, how can we prove that? Since the elements of omega are ordinals, it suffices to prove that this set is transitive. Okay, where's my eraser? It's over here. Okay. So I claim that this collection of alpha W's, it's an ordinal. How can I prove that? I need to check two properties, that when it's an ordinal, if it is transitive and if it's strictly well-ordered by blah blah. Now, over here I can take a shortcut. I can take the following shortcut. The elements of this guy are ordinals. So if this set is transitive, I don't need to actually check that it is strictly well-ordered by the membership relation, because by the theorem we proved last time, which simply said that the class of ordinals is strictly well-ordered, all those properties, like that this set is strictly well-ordered, it would be automatically implied, okay? The point is, if you have a transitive set of ordinals, it's actually an ordinal, okay? If you have a set which consists of ordinals, its elements are ordinals, and if it's transitive, then it's an ordinal. So I only need to prove that this guy is transitive. So let's prove that. Now, let's take an element of this guy, which is of the form alpha sub w, and let's take an element of this. Okay, let's take an element of this guy. So I took an element of omega. I want to prove that this guy is actually in omega, okay? This one's the omega, right? Yeah, okay. Now, by definition, there exists an isomorphism, which I'm going to call G, between this ordinal and predecessors of W, okay? Because that's how I define these alpha sub W's in the first place. Now, this is an ordinal. An element of an ordinal is an ordinal. We proved this, okay? And we also proved that like this is also supposed to be a subset of this. Okay, this is an ordinal. It's also a subset of this. You can easily show that this is actually a proper initial segment of this strictly well-ordered set, okay? This is a strictly well-ordered set. If you just take this guy, this is a proper initial segment of this. Since gamma is a proper initial segment of the strictly well-ordered set, it is of the form. What can you tell me about proper initial segments in a strictly well-ordered set? They are the predecessors of some elements. Now, as we shall proceed, you'll see that every lemma I proved earlier, it's used somewhere, okay? So we're using the lemma over here, which says that if you have a proper initial segment, it is actually the predecessors of some guy. Sorry. It's the predecessors of some, yeah. Okay. Let me explain this. Like, I basically did two things together here, so let me explain that. So I had predecessors of W, and I have this ordinal. There's an isomorphism between them. I took a proper initial segment over here, and I said that this is the predecessors of some element. Well, it is the predecessors of gamma itself. But what I was really trying to get at is, because there's an isomorphism, I can pull this back. Okay, I can pull this back, and this would be the inverse image of gamma under this function. And because this is an initial segment, this will be an initial segment. Because this is proper, this will be proper. Now, if you have a strictly well-ordered set, you have a proper initial segment. This is the predecessors of some element, okay? So let me fix this statement. So this is fine. Yes. So this is of the form predecessors of some element, okay? I think there's a typo in notes. Yes. Okay. Is this understood? And I'm simply going to say now the following. As G restricted to this set, well, if you just look at the restriction of G to this set, this is an isomorphism. Between its domain and its range. Okay? But this means by definition that this W prime is in A, and more importantly, the corresponding gamma is in omega. Okay? Because like this gamma is supposed to be my alpha sub W prime. This is the unique ordinal such that the predecessors of this guy is isomorphic to. Okay? So omega is transitive. Thus, omega is transitive, and so an ordinal. Now let's show that I claim that this is isomorphic to all of A. Okay? Now, consider the following function from A to omega given by W goes to alpha sub W, okay? Over here I'm not looking at the class function, I'm looking at something more specific. Now that I know that this is like by axiom of replacement, I know that this is a set. This is actually indeed an ordinal. I can construct this function, and when I say function, over here I literally mean a function, a set of ordered pairs satisfying blah blah properties. So consider the function which takes each such W to the unique alpha sub W. Okay. So consider this function. So I should put this as an exercise. Check that F is an order isomorphism. Okay? Yes?
Can you repeat how did you show this omega to be transitive? Did you show like something to be its element and subset at the same time?
Yes. Here's what I did. I took an element of this. What do I need to show? I need to show that this element is also a subset. How do you show that some set is a subset of the other one? You take an element of this and prove that it's over here. So I took an element of alpha sub W, and by definition, we have the existence of some order isomorphism between predecessors of W and this alpha W, okay? And I took an element of this. Let me write this. We have that. It's not of this form. That was the type I was talking about. Anyway, I took an element of this. Now, this is a proper initial segment of this guy, because this is also a subset of this. Is the proper initial segment of this. It's closed downwards and so on. You can double check that, like that simply follows from the properties of ordinals we proved last time. And I look at the inverse image of this under this order isomorphism. This is also a proper initial segment because this is an order isomorphism. This is a proper initial segment, so it is of the form predecessors of some W prime. Now I look at the restriction of G to this guy. The restriction of G is an isomorphism between this set and this set, okay? But by definition, W prime is it's in the set A, because there exists an order isomorphism between predecessors of it and some ordinal. But again, by definition, I put all such ordinals in omega. So that ordinal is in omega. So I took an element of alpha sub W and it's turned out to be in omega, which means that this is a subset of this. So any element of omega, it's actually a subset of it. So it's transitive. And now if you look at, let me put this in a little box. If you look at the function from A to omega, which sends W to alpha sub W, it's going to be an order isomorphism. Check that this is an isomorphism, okay? You will actually have to, like you will, I guess, have to use the fact that no well-ordered set is isomorphic to a proper initial segment of itself and so on. This is not difficult. Now, finally, let me argue the following over here in this little space, okay? I claim that this A is actually all of W. Finally, we claim that A is all of W. Towards the contradiction, assume not. Assume that this is not all of W. Then, this difference, W minus A, well, this is a subset of W. If they're not the same, then this difference is non-empty. But by the definition of a strict well-ordered relation, this subset has a least element. Then this guy has a least element. Okay? Let's call it little w. And if this is the least element, then A has to be of the form predecessors of this element, okay? Because any element in here, by this being the least, it would be in A. And conversely, any element in A would be in this set of predecessors, okay? Otherwise, this wouldn't be the least element. But then, let's see. Oh. But then, we would have W in A. Why? Okay, I think, yeah, I need to fix this. There is, again, something wrong over here. Yeah. We would have W in A in this case. Why? Let me write the reason as well. As we would have as predecessors of W is would be isomorphic to omega. Now, if this is an empty, it's the set of predecessors of some element. Well, I just proved that A is isomorphic to an ordinal. If this is the predecessors of W, then by definition W is an A, because A is the set of all W's whose predecessors is isomorphic to an ordinal. Okay? So if this A were the predecessors of some W, then W would be in A by definition. But then this can't happen, which means that this A is not supposed to be the predecessors of some element, which means that A has to be all of W. Okay? But if A is all of W, then I have an isomorphism here between W and this ordinal. Okay? Now, questions about this?
Well, can you define this order isomorphism? Is isomorphism, but order?
Oh, it's supposed to be order preserving, meaning that what's the order relation in here? It's this strict less than relation. So you have to show the following. If A is curly less than B, then what's the strict order relation here? It's the membership relation. You have to show that this is true, okay? If A is less than B over here, then its image is f of A is less than f of B over here. But being less than over here is the same as being a member. So you have to show that this is true. And you have to show that f is a bijection, okay? That f is a surjection follows from the definition of this, because this is by definition the set of all such guys. In order to show that f is an injection, you pretend that two distinct guys are mapped to the same ordinal, but if you have two distinct guys in here, one of them is in the predecessors of the other one, because we're working in a strictly well-ordered set. If you assume that f is not an injection, you would get the contradiction that there's a strictly well-ordered set which is isomorphic to a proper initial segment of itself, okay? Pretend that this is also f of w prime. Either this is in the predecessors of this or the other way around. But in both cases, you would get a well-ordered set which is isomorphic to a proper initial segment of itself, which is a contradiction. So this would be an injection, okay? So showing that this is an injection requires some work, not that much. And then you have to show this, okay? This is not difficult. You have to use the properties of an ordinal number. So I'm just going to assign this as an exercise because it's like routine. Questions about this? No? Are you sure? Now, I have 7 minutes, but what I want to prove would probably take 10 minutes, so I'm just going to take extra 3 minutes of your time if you want, if you allow me. Okay. Yeah, I shouldn't have gone over this again, but yeah, I want to do it. I don't want to edit the videos to fix the little mistakes, so I just leave it as is and just fix the little mistakes by telling you them out loud. Okay. Now this is important. This is notion of Hartog's number. I want to do this on Thursday. So what I'm going to do is I'm just going to make this definition and assign this little exercise. I'm going to prove the theorem later. Sorry, I'm not going to take 10 minutes of your time, okay? So let's have a strictly well-ordered set. By that theorem, it's isomorphic to a unique ordinal. Oh, one thing that I didn't prove over here. Why is this ordinal unique? Because, again, we're going to use the fact that no ordinal is isomorphic, no strictly ordered set is isomorphic to a proper initial segment of itself. Pretend that this, yeah, I didn't write that part down. Well, I don't have space, so I'm just going to mention it. If this were isomorphic to two distinct ordinals, then either this would be less than this or this would be less than this. Pretend that this is less than this. Pretend that beta is less than alpha. Then using the isomorphisms between these two and these two, you would be able to construct an isomorphism from this ordinal to this ordinal, but this is a proper initial segment of this one. So you would get a strictly well-ordered set, which is a proper initial segment, which is isomorphic to a proper initial segment of itself, which is a contradiction. So we're just using that fact a lot in this proof. So this ordinal is unique. So why have I emphasized this? Now, take a strictly well-ordered set. You know that there is a unique ordinal alpha for which you have an isomorphism between this strictly well-ordered set and this ordinal. Unique ordinal blah 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 blah. Is isomorphic to W sub less than is, now you take this ordinal is called the order type of this strictly well-ordered set and is shown by, well, there are different notations for this. I'm just going to write OT for order type. Okay, so every strictly well-ordered set is isomorphic to a unique ordinal. That ordinal is called the order type. So when I talk about the order type of a strictly well-ordered set, or for a well-ordered set, actually, this definition can be generalized to well-ordered sets, not just strictly well-ordered ones. The unique ordinal representing your strictly well-ordered set or well-ordered set is called its order type. Now, everyone remembers the ordinal omega plus omega, which was over here. Let me assign this as an exercise. Consider the relation less than on natural numbers defined as follows. Let's say that a natural number m is less than another natural number n if and only if, this is not the actual membership, actual less than relation on natural numbers, this is like, I'm using curly less than. So m is curly less than n if and only if your sum is even and m is less than n, where this is the usual membership, usual less than relation on natural numbers, or m is even and n is odd. Okay? So I give you this relation, and I'm also giving you that this is actually a strict well-ordered relation on the set of natural numbers. This is strictly well-ordered. Now, your exercise is to show that the order type of this strictly well-ordered set is omega plus omega. And I want you to do this by as follows. Find an isomorphism. between these two, okay? Now, this relation, like the definition might look complicated, but this is really easy actually, because let's try to understand this relation. Apparently, m is curly less than n if m is even and n is odd. This is one possibility. So somehow all even numbers are less than all odd numbers. So I'm just gonna draw this line. On the left, I'm just gonna put even numbers, and on the right, I'm gonna put odd ones because odd ones are supposed to be bigger. This is one possibility. What's the other possibility? The other possibility is that m is actually less than n with the usual relation, and their sum is even. When is the sum of two natural numbers even?
Both of them are even.
Both of them are odd. Good. So let's pretend that both of them are even. If both of them are even, then this is true, and this relation between them holds if and only if m is actually less than n. So I have that, for example, 0 is less than 2 because they're both even, and this is actually less than this. 2 is less than 4, 4 is less than 6, 8, and so on. So I have I have these even numbers, which are ordered like this. Now let's pretend that both of them are odd, both m and n are odd. Then this is satisfied, and m is curl less than n if m is actually less than n, when they're both odd. So I have this picture as well. One is curly less than 3, which is curl less than 5, which is curl less than 7, and it goes like this. So these elements are ordered like this, these elements are ordered like this. And I know that by the second scenario, by the second possibility, all even guys are less than all odd guys, okay? So this is the picture of my strictly well-ordered set. I have 0, less than 2, less than 4, less than 6, dot, 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 dot. I have all the even numbers, all of which are less than 1. And 1 is less than 3, which is less than 5, which is less than 7, dot, dot, dot. So this is the picture of my strictly well-ordered set in this case. Now show that this is isomorphic to omega plus omega. It kind of looks at least pictorially obvious, right? What is omega plus omega? It's the ordinal 1, 2, 3, dot, 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 omega, successor of omega, successor of omega, dot, dot, dot. This is the ordinal omega plus omega. And this is a set of natural numbers ordered with respect to this relation. Well, pictorially, it's clear what you're supposed to do, right? You're supposed to map this to this, this to this, this to this, this to this, omega to this one, and so on. So what I want you to do is, like pictorially this is true, as you can see. I want you to write down the actual isomorphism between this set and this set. Define the map, f goes from blah blah to blah blah, write down the rule, and check that it's an isomorphism using the definition. It's tedious, it's boring and it's long, but I want you to double check this so that you will have practice checking that some map is an ordered isomorphism. But pictorially, it's obvious that this well-ordered set is isomorphic to this well-ordered set, right? Okay, that's good. Now, you remember I told you, like, when we introduced well-ordered set, I'm not going to give you many examples. I could have given this example, and at that point you would be able to check that this is a strictly well-ordered set, but I told you that, like, we're not going to do that because we're going to be dealing with ordinals most of the time of this course, and ordinals are basically, they're all well-ordered sets. Okay? Which is proven by this theorem. Okay, that's that. Any questions about this? Now, let me tell you what we're going to do next lecture. We're going to prove that, we're going to introduce the notion of an Hartog's number, and we're going to show that uncountable ordinals exist, and we're going to name the first uncountable ordinal omega 1 and probably talk about it, because even if you're not going to do set theory in future, that ordinal omega 1 will show up in various places, such as topology or sometimes functional analysis or measure theory, okay?